you. Thanks for the introduction. It's really good to see all of you in the very final session of Spark Summit. I'm excited to be here talking about this. You're very patient. You're here in the last session, and I hope you'll find something interesting to take away. Unfortunately, we've all been there, stuck in traffic with rain pouring or snow, and we all find something to relate through this talk, and you'll find something useful that you can take away with you. With that, I will start talking about the work we've done. And at a high level, this is the agenda of the talk. We built a machine learning system to predict traffic using weather as an additional feature. And if you've been through some of the talks in the last few days, this is the standard process that you would expect. We had a business understanding a problem that we wanted to solve. We went about getting the data required for it and doing the appropriate feature engineering in order to suit the problem that we have at hand. And we tried a few models, and we put into production the model that we think works best. And through the rest of this talk, I'll be sharing with you some of the experiences we've had, some of the things we've had to build along the way in order to make this work with Spark, and share the results we have. So to begin with, what is the challenge itself? So for any of us that live in a city like New York City, like myself, or London, or San Francisco, or any large metro for that matter, the problem of congestion needs no introduction. We've all been stuck in traffic. And with statistics such as 36 billion hours being wasted on trucks that are stuck on roads, and average citizens like myself losing about $800 per year on wasted fuel and time, this translates to a lot of dollars lost for companies. Not to mention the frustration and apparently the expanding waistlines that we all get when we sit in traffic. So we definitely don't want that. We want to do something about it. So ideally, I want to solve the problem of congestion and make sure there's no more congestion on the roads, but that's not what we are doing. Hopefully, there are people working on that problem. This is not a talk on how to fix congestion, but rather this is a talk on if you have to plan for congestion, how do you manage, how do you plan and help yourself be less frustrated along the way? Now, what we do towards that is just imagine something like this showing up on your phone saying that, hey, there's a snow forecast for later today at 3 p.m., and I know you have to be home at 5. Maybe you have some appointment. You don't want to get your spouse upset. Your dog needs to be taken to the vet. I don't know. But you get this nice alert on your phone that says you need to leave now if you want to make it to your appointment by 5. And some of us might be using apps like this already to plan for our commute. But what we've seen, what we'll show, is that these estimates go horribly wrong when you have some adverse weather impacting your traffic. And that's what we wanted to fix in this process. So think of an app that lets you look at various times you can leave so that you know how much time you want to spend and accordingly plan your travel times so that you minimize your frustration to some extent and save some of those dollars that are wasted. Now, before I go and tell you how we solved the problem, there was a traffic survey that was done. So just a little step back, you'll see Weather Company all over this slide. So Weather Company is the traffic company that IBM acquired a couple of years ago. The company itself I learned it's as old as me, and that's all I'm going to say about it. The company was acquired by IBM 2 years ago, and you might know about it through the weather.com or Weather Underground. These are their websites. So all the traffic data we get is through this company called the Weather Company. And to convince ourselves, and most importantly, the people that are funding us to do research that we're not wasting our time, there was this traffic survey that checked with people how often they check traffic before they start their commutes and how often they check their weather. And as it turns out, 2 out of 3 people plan for their commutes before they actually start the commute. And as many people check what the weather is before they leave. And people surveyed or were also willing to change their travel times or routes if we told them that the weather was bad and their commute would be affected. So this is to just a sanity check that we were taking the right approach to solving the problem. So to summarize, we know that there are general traffic patterns. We all know that weekends are better for commutes. We all know to avoid rush hours. But what we wanted to do was quantify this effect weather has on travel times. For this, what we did was to select 5 unique cities in the US. They were unique in terms of their size and how spread out traffic is, what's the density, and how much people commute. And on these, we analyzed data for 1 year on both traffic and weather, which for the 5 cities comes out to 2.5 billion traffic records and 260 million weather records in 1 year. And in order to analyze this data, this is a large amount of data, and this is for 5 cities. So if you want to provide this as a service, and we want to scale out, Spark was a natural fit to our solution. But in order to make this work with Spark, there were several extensions that we had to do, which I'll be talking about shortly. And we're talking about data that's temporal in nature, has temporal correlations. There is a geospatial component attached to this data, so we had to build extensions to all of that. And with that, we built cognitive models that predict future traffic flows, starting from 15 minutes into the future all the way up to 24 hours into the future. So next in this process is the data itself. And I call this data collection, although what I'll be talking about is the description of the data we had. As I mentioned, we get the weather data from the weather company whose business it is to curate and forecast weather for curate weather for the next 10 days, and they're very good at it. Their forecasts are known to be one of the best in the market. So I work for IBM, and we have access to this data because of the purchase 2 years ago. This is also available for people if they want to work with weather data. And in order to build machine learning models and do predictions, we had to work with 2 types of data. One is archival. This is in order to look at years' worth of data and build models on the history. And the other is the forecast. This is what the weather company does, and look at the past data and provide forecasts for the future. So weather is available you're able to query weather for a given bounding box. So for a city, we are able to provide a bounding box and get access to all the weather stations that are within that bounding box. And it gives us various weather parameters like, obviously, things like temperature and rainfall and snow. And things that were not so obvious, such as the glare of the sun and the road surface temperature. This is something we learned to not ignore anything that's non-obvious. There was a lot of snow, and we saw that people were driving at 2x or 3x the speeds, and we thought there's something wrong with the data. But as it turns out, the surface temperature is really important to take into account, because if the snow is not sticking to the ground, people are the roads are clear, everybody's at home thinking there's too much snow, we don't want to drive, and the ones who are there are able to make it much quicker than usual. So some of these beats your intuition. We have to go back, look at the data, and understand what really happened. The traffic data is something we actually procured from an external vendor. It's called INRIX, which we have a collaboration with, and some of this work has been shown at the NAB summit that happened in Las Vegas some time ago. INRIX is actually an external vendor that works with traffic data. They collect data from various sources, including sensors on the vehicles. This is something like Waze, where people go and it's crowdsourced and people go and enter what's happening. But they're also working with other sources, such as the road sensors and the speed sensors on road and so on. So they have data for, they say, 8 million kilometers of road in the United States. They have archival data, again, in order to look at history, and they have real-time flow that's coming in. And we have very fine granularity of traffic data for this. They provide us with what is called as XT segments, which range from 100 to 350 meters long, and we are able to make predictions at this granularity. So as you can imagine, this is a lot of scale if you're looking at 100-meter roads in a country like US, and you want to scale it up. OK, so here's what we have. We have data with different modalities. We have the traffic data with history and the real-time traffic. You want to obviously predict what is the future traffic going to look like. You have weather data from the history, and you also have weather forecasts for whenever it is you want to make your traffic predictions. And through INRIX, we also have access to incidence reports, which could be things like road closures and accidents. So you can plan your model according to planned incidents, or if there are some intersections where accidents are most prone at certain time of the day, you can take these into account in your model. So on this, we use Apache Spark to do our training on the archival data. And as I mentioned before, we have to create extensions to handle time series and geospatial data on Apache Spark, which I'll be talking about very soon. And in these training models, we started with something simple. We looked at first-order models, such as ARIMA or BATS for simple time series forecasting. And the results were not so good, so we looked at better prediction models. We looked at random forests and LSTMs, and we realized that there's a lot of correlation in this data. There's, it's a road network. There's a rich correlation of what causes what. So we wanted to take that into account, which all led us to build some extensions for feature engineering. And using these models, we built a real-time scoring system, which I'll talk about how it's going to be used eventually, but you can think of it as if somebody wants to find out what is going to be the commute time at a later stage, you use the scoring function on a built model and use this for your computing your total commute time for this route. Okay. So, first, I want to spend some time talking about the extensions that we did for the for Spark itself. So both traffic and weather can be thought of as time series data. Both of them are events that are being continuously sampled, and you're taking some measurements. So for each timestamp, you have an observation, which could be the temperature, or it could be the speed on the road. So both of them, at some frequency, they're being sampled continuously. And both of them have temporal dependencies. So if you think of what time series data is really, you have this process that's being sampled, but they also show dependencies in time. What happened today has a lot of correlation with how the weather was yesterday or a couple of days ago as compared to what it was 6 months ago. And same thing with traffic. If there is an accident, for the next few minutes or hours, you can expect the road to be congested. So there's a lot of such temporal dependencies. There's also seasonal patterns. Whether you look at traffic or weather, you know that there is seasonality in terms of rush hours and weekday, weekend seasonality. Similarly, with weather, you have seasons. And as a result, we needed a suite of extensions in order to analyze this kind of data on Spark. And in order to do that, in the process of doing that, what we realized was that what was lacking truly was this extendable library that needed to be built on Apache Spark to handle these kind of time series data. And this is something we went ahead and built, and since then has been used in other applications that are completely unrelated with weather or traffic prediction, because we built this generalizable library. So first was providing scale out. So we realized that there are some applications in which data is embarrassingly parallel. There are a lot of short time series that need to be analyzed. They all fit in each of them would fit into the memory of a single machine. But there's so many of them that you want to parallelize, and you use Spark to do that. And some of them are not so parallel in the sense that the data might not fit into the memory of a single node. This is a single time series that has to be spread out across several nodes. And in a distributed manner, you might want to compute your algorithms on time series, which is a lot harder because now you need communication in between your Spark nodes. So we built two types of RDD, short and long time series RDD, in order to address these problems. The other extendable thing we did was to make it fully type templated. So mostly time series data in the financial world have addressed double values. It's a continuous process that's measuring something. But in our case, we were looking at a lot of IoT data. And in general, not all applications produce double values. So we wanted to deal with maybe sensor actuations, which are on-off, but it's a time series of sensor actuations. You could have a time series of geolocations that your GPS is sampling, and we wanted to support that. So it was fully templated with support for all data types. And we needed to provide other kinds of windowing. So what Spark provides is a record-based windowing, and the sliding transform in the RDD. But that was not enough for us because you might want to do time-based windowing. So I want to say, run this aggregate for hourly or daily or weekly. And these primitives needed to be added. And especially in the case of a distributed RDD, your hourly window could be within the memory of a single node, or it could stretch across multiple nodes. And we had to be careful about looking at other partitions and not doing a full shuffle and efficiently implementing this. Further, we also provided what we call as an activity-based windowing, which again makes a lot of sense for IoT applications. So think of how a sensor might work. Most of the time, it's sleeping to conserve battery. But when there is an event, it turns on, it measures something for some time, and then goes off again. Think of a microphone, for example, acoustic sensor that you deploy. So what we wanted to do was provide a primitive which would segment the time series based on this activity. So it would detect bursts automatically, and you could specify a window around that burst or an anchor point, and it would let you do analysis on these kinds of windows. I won't go through the entire list in the interest of time, but one more thing that we needed to do was to support a different kind of join. So Spark has a lot of joins, but what we realize is missing is this concept of temporal join. So sensors are measuring data, right? So in our case, there was traffic and weather data, and you get weather data once an hour. We get traffic data 4 times an hour. And you want to join this in order to have some kind of multivariate time series. And in the case where there is no timestamp that's matching, your join will not work. So say they're off by 10 seconds, your join is not going to work. So what we had to specify was be able to provide a window of time, saying join any value which is within 10 minutes of this, and have Spark look for those values within those boundaries and do a join. And in the example that I just gave, where you have 1 value in one case and 4 values in the other, you want to specify something more, maybe a lambda that tells you take the average of these 4 values and then join. Or in the case of, say, rainfall, you might want to add them and take the sum and then join. So we gave a flexible lambda here that lets you join however the application writer wants to join. And the reason I'm dwelling on this is hopefully soon we'll have this available. So we're working on the paperwork that needs to be done for open sourcing this library. And we hope very soon it will be available to the rest of the community. And we want to make sure that people use this and give us feedback. Hopefully you'll find it useful for your applications. Because some of these things we realized when we were working with Spark were things that were missing and we had to build. And finally, we had to build several statistical and data mining functionality on top of these RDDs in order to do time series analysis itself. You'll find simple things going from statistical modeling, linear modeling such as ARIMA, to trend analysis. You might want to forecast on time series that have seasonality, so you might want to use Holt winters or bats. We also have data mining algorithms there, such as k-means and k-shape. And the out-of-the-box k-means will not work on a time series because you have to define what is a distance metric for two time series. You have to be able to define, if I give you two weather stations and ask you, are these two weather stations similar, you really need a metric to measure what does it mean for these two stations to be similar. So we had to implement time series metrics such as DTW, and we've provided these. And using these metrics, we have some unsupervised techniques that people can use for clustering. So it's known, we've used this for applications as diverse as are two weather stations similar to are these two impalas moving somewhat similarly. So one was a time series of double values and the other was geolocations. And the framework works for everything because it's meant to be extendable. Okay. So I'll briefly talk about some of the machine learning algorithms we used and how they work. This is not a primer on machine learning by any means. It was just a learning experience for us on how the scalability works and what we needed to build to make these algorithms work. So like I said, we started with something simple first. This is ARIMA, which is autoregressive integrated moving average, which people use over a stationary process in order to predict the next value. What we did was for each of these road segments, we built an ARIMA model. And because we have Spark to our advantage, we were able to parallelize this job completely. To give you an example, a city like Chicago would have about 3,000 to 5,000 segments for roads that are just freeways. So there's a lot of data that needs to be run in parallel. And what we found was that it was as expected. It's not the best model. We get an accuracy of 75%. And the time here may not mean much to you. It takes 3 minutes to run the model. But it'll make sense once we look at how long it takes for the others. This is all for one particular city that I'm talking about. And data was completely scaled out, and it was embarrassingly parallel, so no two jobs had any data that was shared between them. So this was as fast as it could be. And we see that the accuracy is quite bad. And when it's bad, it could be 4 times, we could be 4 times wrong, which is not great. So we moved on to some of the more successful machine learning models for regression, and specifically random forests. So random forests are an ensemble of decision trees that reduce the problem of overfitting. And it really worked well for us because decision trees are able to handle both continuous and categorical data, and weather could have categorical data at times, or roads too, such as open and closed. So we leveraged Spark to parallelize this random forest building. We have a random forest built for each of these segments. And for features, we have the speeds on the current road segment, the weather on those road segments, and as it turns out, this is the spatial correlation I was talking about. So the speed on a current road has a lot of correlation with what else is happening nearby. So we needed to find out what are these other road segments that are correlated with my current road segment, and add more features which had from these other connected road segments. So we used several ways to find these correlations. One was spatial radius. Given a road, tell me what are the roads within 5 kilometers, which required geospatial extensions to find the nearest neighbor for these segments. We also needed correlation and causality to work. We have correlation and Granger causality built in, and we use the time series RDD to parallelize this. And as expected, this works much better than the previous case. As you can see, the accuracy went up to 82% without using any weather, but on using weather, it went up to 89%. And now the time has gone up simply from the fact that this is a more, it's doing more complex operations, and there is this additional correlations that exist, and it's not as parallel as it used to be. There's data from other RDTs that are required. So Spark is doing a lot more in terms of going across partitions. slides. So that worked quite well. We have close to 90% accuracy, and we could have stopped here. But I work in research, so why stop at something that works well, right? So we have to go and explore other models which may not work. So we wanted to look at how to use deep learning in this problem. And on a more serious note, there were a few problems with the previous approach. One, and the most important being that the correlations were hand-selected to a large extent. So I say, hey, look for correlations within 2 kilometers, which may not make sense because one freeway might be crowded and it might be affecting another freeway that's 10 kilometers away, but those are the two main segments for your commute. So you really don't know what is this best correlation. And when we tried to run something like Granger causality across all road segments, the RDD DAG got so big that it just wouldn't run. So we had to somehow pare down what kind of pairwise correlations we were working on and maybe only look for correlations within a certain radius. Again, things got a little manual at that point. So we wanted to move away from these processes and discover the correlations in a more unsupervised manner. So we looked at node embedding as an approach. So you can think of road network as a graph, and you can use node graph embedding techniques in order to find an embedding for your road network. So what that means is you have a graph, and what is the nodes that are close within the graph are going to be represented in a vector space such that these nodes are also close to each other in a vector space. And then we use this vector embedding in order to train our recurrent neural networks. We used LSTM's long short-term memory, a variant of recurrent neural networks, in order to run our regression because it's known to solve the vanishing gradient problem that occurs with RNN. But it's been well tested in the field of linguistics, and we applied it for our regression here. And this is work that's ongoing. We have good results, but how to create the vector embeddings and how to get good regression results in a parallel manner is something that's ongoing. And actually, hearing about tensor frames and graph frames for the last 2 days has helped us refine the solution a lot more. So this is something that we are going to be working on for a bit. So finally, so those were the models that we built. And just to recap, what we had was this traffic and weather data, which required us to perform temporal and spatial joins. And we have this lambda architecture here. So this data is going to archive here. Think of this as a data warehouse, which is then going to be used. Spark is going to look at this archival data and build models on a regular basis. And the top part is not happening too often, especially if we use something like LSTMs, which takes a few hours to train. This might be something, your traffic patterns might be changing once a month or once in 3 months. And you really want to learn this model for a long time and keep reusing it. And at the bottom, you have really your queries that are coming in real time. So each time there is an update for traffic or weather, think of it as every 5 minutes, we have a new update for what's the current traffic or current weather. It's going to show up as an event in Kafka. Streaming is going to pull that event, compute, score against the models that are created. And then you're going to have it in a key value store that your APIs could then interface with. So you might build a REST API which takes in a whole route and looks up the segments that belong to that route and compute the time it takes for your route. So what does it all finally result in? Do we save commute times? So we saw, using these prediction methods, quite a bit of improvement across all geographies. So these are the 5 cities we used in our prototyping. And since then, we've expanded the study itself to 10 more cities, and the architecture you just saw in the previous slide is going to be scaled up to 100 cities very soon and being offered as an API from IBM. But we saw, especially during rush hours, 40% improvement in accuracy is pretty good. And we are working continuously on how to make these numbers look even better. And that's what I have. So, we believe that predictive traffic will significantly impact how people plan their day, and give them better times to commute, or help businesses save money by scheduling their trucks better. And please watch this space, or send me an email if you would like to be in touch about the open sourcing. We really hope it will happen sometime this year. Thank you.
Thank you, Ramya. Do we have any questions from the field? We have microphones to the left and right.
I have a question. So, thanks for your talk. It's I feel very interesting about your node embeddings by using LSTM. Can you please give me more detail how do you abstract your data into a graph representations?
Sure. There was, I believe it was a KDD 2016 paper called Node to Vec from Stanford, which is what we started with. It does a random walk on the graph, and it varies between DFS and BFS. So when you look at your graph, right, you have two kinds of similarity. One is called the homophily, which is nodes that have a similar structure that look alike, and you have structural isomorphism, which is you might be far away in the graph, but you look structurally the same, versus you are actually close by in the graph. So these are two kinds of similarity that you have to embed in your vector space. So they have an algorithm where they're able to vary these two knobs and do a random walk on the graph and come up with an embedding. So we started from that, but we found out that these work well for social network graphs, not so much as when we tried doing it on cloud networks. It didn't work all that great, so we are working on how to do it better. But if you write me an email or something, I can hook you up with the paper and give you more details.
Thank you.
Sure.
Thank you. Any other questions? Yeah, feel free. Or
Do you have any idea why the method perform much better in Chicago than Atlanta, for example?
Let's see. So, yeah, Chicago has much worse weather. They have more snow than Atlanta. Atlanta is geographically quite far away from Chicago. So we found out that these results are sliced and diced in a way such that it shows the effect of weather more pronounced in the results. And in cities that don't have a lot of adverse weather conditions, you'll see less improvement. We just feel there's less to improve.
all right, that's all the time we have. One more question.
One more, yeah. For example, you mentioned DTW, which is probably quite expensive to compute. Did you work on distribute these algorithms, or?
No, that's actually a great question. Yeah, we want to distribute DTW and K-shape. We have not done that yet, so they run. You're able to do it. Yeah, it's not distributed in the way that you're asking, right? Yeah, we don't have distributed implementations of those. Yeah. Hopefully, once we open source it, we'll get more people to look at it. Yeah.
Okay, thank you, Rama.